Hey everybody, in Calc BC. Today we are starting our Unit 6. This is going to be lesson 6.1. It is called Sequences. Now, College Board's Unit 10 is drastically different than any of the other content we've learned so far in calculus. And because there are, 15 different breakdown topics that College Board has defined, we are actually going to split this into two different units. This is going to be Unit 6 and Unit 7. Our Unit 6 is going to focus on the first 10 lessons here from College Board, and this is going to be the overall theme here is series convergence. And so a series is like a series of numbers that are added together. A sequence is then just a series of numbers. A sequence is just a set of numbers. And so today's topic is actually going to be just on what a sequence is before we actually get to series. So this is kind of like a sub lesson of lesson 1 from College Board's breakdown of the content. So you can see down here in topic 10.1 from College Board, we have the nth partial sum is defined as the sum of the n terms of a series. An infinite series of numbers converges to a real number s or has sum s if and only if the limit of its sequence of partial sums exists and equals s. So there's a lot going on here, and that's why we're going to break this down into multiple lessons. So really, the goal today is just to be confident in what a sequence is, and you can see that the term convergence is coming back. So we just talked about with improper integrals, the idea of convergence. That's coming back here. We're going to focus on sequences today, make sure we're comfortable with those before we even bring in the idea of a series, which will be our main topic this unit. So let me go ahead and pause and we'll switch over to the notes. All right, so here are our notes. And up first, we just have some new vocab and the like to go over. So a sequence is a function whose domain is the set of positive integers. This sequence a sub 1, a sub 2, a sub 3, etc. is symbolized by, in curly brackets, a sub n. The subscript n is always understood to start with 1 and to include all of the positive integers. There's two different main types of sequences that we're going to talk about, and that's an arithmetic sequence versus a geometric sequence. Yes, this is also the word arithmetic, but when it's used in this context, we pronounce it as arithmetic. It's an arithmetic sequence. So you can see here we have 3, 8, 13, 18, and you can tell there's a difference of 5 for each of these, right? So whenever we're adding or subtracting, that's called an arithmetic sequence. And I'm going to actually write that down. Add or subtract. And the nth term of an arithmetic sequence, if we consider the difference to be d, it would be whatever a sub 1 is plus d, the difference, times n minus 1. Okay, so in this case, we would have to know what the first term is, and then we have to know what to add or subtract each time, and that would be going here. All right. Next up, we have 5, negative 15, 45, negative 135, and you can probably tell that we are multiplying by negative 3 each time here, and that's called a geometric sequence. Geometric is when we multiply or divide each time, and we have this common ratio that's called r. And the nth term of a geometric sequence is just a sub 1 times r to the n minus 1. And so for the first term, 1 minus 1 would be 0. So we wouldn't be multiplying by anything here. This would be r to the 0 power, or just 1. So that would just give us the first term, a sub 1. And then for each term after that, negative 3 would be multiplied, in this example, a certain number of times to get us to that term. Okay. Some sequences are neither arithmetic nor geometric, such as these. If we just have n squared, 1, 4, 9, 16, there's no common difference or common ratio in that example of a sequence. Same thing for 3 to the n plus 1, and same thing for 2n minus 1 over 3n plus 1. You can get kind of creative with the way that these are defined, and again, they're not always just adding or subtracting or multiplying or dividing the same number every time. The important thing is that we are able to define what the pattern is in some expression that has n in it. Okay, so if a sequence has a finite limit as n approaches infinity, we can say that the sequence converges to that limit. If a sequence does not have a finite limit as n approaches infinity, then we would say that the sequence diverges. The sequence might diverge because the terms are increasing without bound, or because the terms are decreasing without bound, or because there is just no limit as n approaches infinity. Maybe it bounces back and forth between some values. But what's important here is that when we were doing improper integrals, and I showed you the example of like a series of fractions being added together, that's what we call a series. Series is when we're actually adding the terms of a sequence together. But in this notes lesson, since we're talking about a sequence, the sequence converges if the terms themselves approach a certain number. So we're not adding any of these together. We're just saying as we move along this set of terms that's in this sequence, do the terms eventually approach something? Okay, so that's kind of what we're talking about here. So let's try some examples. Determine whether each sequence converges or diverges. If the sequence converges, find its limit. If the sequence diverges, show why. So in this question, first off, we have the sequence defined as 1/2 to the n minus 1 power. And you can see that as we go, the denominator is doubling every time. Since that denominator will just continue to grow, there's no reason. Hold on, let me write that down. So the denominator continues to grow. Since the denominator continues to grow, these fractions are going to be approaching 0 over time. So we would say that this sequence converges to 0. Another way that we could think about this is the limit of the sequence notation here. So it's the limit as n approaches infinity of the sequence term. And that indeed does equal 0. So it makes sense, right? Because that denominator is just going to continue to grow. The numerator is going to stay 1. All right, let's try letter B. We have 1, negative 1/2, 1/4, negative 1/8. So this time it's pretty similar to A, but the negative switches, well, the sign switches every time, right? Because we're multiplying by a negative. And in this case, we could write it as the limit as n approaches infinity of negative 1/2 to the n minus 1. But what's important to realize is that we don't have to only be approaching a limit from above or from below, right? It doesn't matter if we're like approaching 0 from above or approaching 0 from below, or if we're approaching it from both sides. Like if we kind of plotted these points on a graph, I guess I could make a rough sketch over here. We would have, you could say 1, and then negative 1/2, and then 1/4, and then negative 1/8. And we're like, if we kind of think of each n as being the x value and then plot these values as the y values, so you can see like over time, we're jumping over the x-axis, but we're still approaching 0. So this still equals 0 because over time, yeah, we're kind of approaching it from both sides, but it's still converging to 0. So we would say converges to 0. Let's look at letter C. A sub n equals 3/5 to the n. This time we weren't even given any example terms of the sequence. But let's see if we can figure this out. The limit as n approaches infinity of 3/5 to the n. And that actually does equal 0. And let me tell you why with this little rule down here. So this converges to 0. And the rule has to do with the r. So if we kind of come back up here to this definition of a geometric sequence, the rule is that if r is less than 1, the absolute value of r, then the geometric sequence we would say, converges to 0. So the trick is, can we make this example in letter C look like that definition up there? So it's a sub 1 times r to the n minus 1. Okay, and this fraction is to the n. So it doesn't actually look like this yet, but what we could do is say, if we wanted to get fancy, 3/5 to the n would be the same thing as saying 3/5 to the n minus 1 plus 1, right? Because all we're doing is subtracting 1 and adding 1, so that doesn't really matter. And then we could write this as 3/5 to the n minus 1 times 3/5 to the 1, right? Because anytime you have added exponents, you can multiply by a new base with the new exponent, right? So this is really 3/5 times 3/5 to the n minus 1. So all of that to say, the number that we're multiplying by every time, which we knew from the start, is 3/5. If we wanted it to get in this actual notation, there it is. The first term is 3/5, and then we're multiplying by 3/5 for every subsequent term. And so the point is that r is 3/5. Since we are multiplying by something that is less than 1, the absolute value of 3/5 is less than 1, it's going to shrink every time. So it's always going to be approaching 0 over time, right? If you multiply by something between 0 and 1, your answer is going to be smaller than what you started with. It's going to be, in this case, 3/5 of what we started with every time. So it's eventually going to approach 0. The terms will approach 0. What about letter D? A sub n equals 5/3 to the n. If we wanted to know the limit as n approaches infinity, let's just think about what's going to happen when we keep multiplying by 5/3. Maybe for this one, I'll actually show this on the calculator. So we just start with 5/3, and then we multiply by 5/3 every time. What you will see is that our answer is going to just keep growing faster and faster, right? So this does not converge to any specific value because we're multiplying by something greater than 1. So the answer is going to keep growing. So as we keep going, we could probably, well, we definitely could express each of these as a fraction, but you can see even in decimal form, they're going to keep growing and growing and growing, right? So this approaches infinity, and so we would say that the answer is that it diverges. The sequence diverges over time. And in general, the rule is that the absolute value of r, if the absolute value of r is greater than 1, then the geometric sequence diverges. All right, we have a couple more examples on the back. Letter E, a sub n equals sine of n. All right, so for this one, usually the numbers that we plug into a sine function are in terms of pi, right? But in this case, the terms of this sequence would actually be sine of 1, sine of 2, sine of 3, sine of 4, sine of 5, etc., right? That's what this sequence definition means. And I don't think I can write this as arithmetic or as geometric. It just doesn't work. You can't multiply by something each time and expect to get these answers. You can't add something each time and expect to get these answers. I'm going to switch over to Desmos for 1 second so that we can examine this on the graph. All right, so what I'm going to be doing is kind of showing you the graph here that represents this sequence. So again, we're looking at letter E, which was just sine of n. So first I just graphed sine of x just to remind you what this graph's going to look like. It's a wave function. It goes on forever. It oscillates between a y value of +1 and a y value of -1. Oscillate just meaning that it's going to continue to bounce up and down between those values, right? And our sequence is specific y values from this graph, and it's going to be the y values starting with a positive value of 1. Sorry, the x values with a positive value of 1 and continuing on, and whatever y value corresponds to that x value is a part of our sequence. So what I've done here, and you can feel free to take notes on, what I've entered into Desmos so that it will actually create a sequence. But you can see when I enable this plot, which the ends, I just chose to graph from 1 to 100, and a sub n is just sine of n. So it's graphing for every whole number x value, it's graphing the sine of that x value. So we've got all these green points now on our graph, and if I disable the original curve, these points represent our sequence. And over time, what we would want to see if this converged is that these would approach, say, 0, right? So these will get closer and closer to 0 over time. Now, some of these points do get closer to 0. Like this one looks like it's almost directly on 0, or on the x-axis. But that just keep bouncing up and down eventually. And now they're not necessarily following a specific pattern that's easy to, find the values of, right? It's not like we're plugging in pi over 2 and then pi and then 3 pi over 2, because we know those y values on this graph. But it's actually the whole numbers. So it's going to be weird decimals, but over time, the values don't actually approach anything. They just keep bouncing or oscillating between y values of -1 and 1. So this actually diverges. Even though the terms don't get bigger and bigger, the terms don't get smaller and smaller, they just never approach one single value. They just keep bouncing up and down. So that's what I'm going to go back to the notes and write down. All right, so I went ahead and filled in the rest for letter E. I said that the values bounce, or you could say oscillate, between -1 and 1 infinitely. Now they don't just go 1, -1, 1, -1, 1, -1. They actually have these weird decimals that we're not going to investigate much further, but they're always between -1 and 1. And because of that, we don't approach one value. There is no limit, so this diverges. Okay, letter F. A sub n equals 3n plus 2 over 5n minus 1. This is another one of those sequences where we can't write it in arithmetic or geometric form. So I'm just going to consider the limit as n approaches infinity of this fraction. And it's going to be helpful for us if you remember Bobo-Botten eats DC for this type of situation, right? Bobo-Botten eats DC tells you if you have any horizontal asymptotes that your curve is going to approach when you have a rational function, which is a fraction of polynomials, which is what we have here. So let me just write that down quick so that I remember. And the idea is that if our exponent or our degree is bigger on the bottom, then the horizontal asymptote is 0. So our degree on top is 1 and our degree on the bottom is 1. So we're not bigger on the bottom. Botten means bigger on top, then it would be none. And we're also not bigger on the top. So it must be the third case, which is eats DC. So its exponents are the same, which is what we have. Divide coefficients. So it's going to be 3 over 5. Another way that you could figure that out is by using L'Hopital's rule. But I like to just go back to our good old Bobo-Botten in these cases. So this fraction is going to be approaching 3/5 as n approaches infinity. So what we would say then is that we converge to 3/5. All right, let's try the next one. Letter G, a sub n equals 3 plus -1 to the n. So in some cases, it's just easiest if we list out some of the terms so that we can tell what's going on. So let's just try plugging in different values for n. So let's see if we have a certain n, what is the a sub n going to be? I'm going to try the first couple. So if I plug in 1, we're going to have 3 plus -1 to the first, which will just be -1. So 3 minus 1 is going to be 2. If I plug in 2, -1 squared is +1, so we'll have 3 plus 1, so it'll be 4. For the third term, this is going to become negative again, so 3 minus 1 will be 2. For the fourth term, it'll become positive, so it'll be 4. And that pattern is going to continue, right? Because every exponent switches between odd and even. So this switches between +1 and -1. So you can see this is actually bouncing between 2 and 4, 2 and 4, 2 and 4. It's never approaching one number. So that means that it diverges. Let's see if we wanted to expand on that. We could say values bounce between 2 and 4 infinitely, similar to letter E. All right, let's keep going. Letter H, a sub n equals natural log of n over n. And I'm gonna write out the limit again, because again, this is not arithmetic or geometric. And it's also not gonna be super helpful if I just start listing the first few terms this time, because natural log of each of those numbers isn't gonna be a nice number. So I'm just gonna write that out as a limit. And what I notice is that as n approaches infinity in the numerator, we approach infinity, and in the denominator, we approach infinity. And I'm gonna actually write this out the proper way that you would need to if this was a quiz or an AP test in order to be able to use L'Hopital's rule. So we would have to separately find the limit as n approaches infinity of the numerator and the limit as n approaches infinity of the denominator. And we can say therefore, I use the 3 dots to mean therefore. We can say therefore L'Hopital's rule applies. You want to make sure that you don't write that it equals infinity over infinity. That would not be the proper notation. But anyway, so let's keep going. So this is going to become the limit. As n approaches infinity, we take the derivative of the top and the derivative of the bottom. The derivative of the natural log of n is 1 over n. The derivative of n is 1. So this just became the limit as n approaches infinity of 1 over n. And I know that as this denominator continues to grow and the numerator stays 1, our fraction is going to approach 0. So this means that the original sequence converges to 0. All right, one more, letter I. This one has some factorials. So we have a sub n equals n plus 1 factorial over n plus 3 factorial. Factorial is a pretty common math symbol, this exclamation point. And I do remember that sometimes Calc BC students, it's been a while since you've seen this. It comes up in probability. So if you've taken statistics, you probably have seen this. And I believe you learned some combinations and permutations in middle school, which would use this notation, but I'm not sure. But really what it means, and I'll just kind of do this below here, we have this idea of a factorial. And if it was, for example, 5 factorial, it means you multiply by every whole number from 5 down to 1. And if it was 1 factorial, the answer would just be 1. If it was 10 factorial, we'd have to do 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, in a question like this, let's say that we were given something like n factorial. We could expand that by saying it's now n times n minus 1 times n minus 2, etc., down to 1. Because you can see I'm like subtracting 1 each time, just like I did in the first example here. And so oftentimes when we have factorials in fractions, there are secretly a lot of terms that we can cancel out to make our fraction look nicer. So in this case, I will help us out here. The top is just going to stay as n plus 1 factorial. The bottom we can rewrite. So n plus 3 factorial could be rewritten as n plus 3 times n plus 2, right? Because if we subtract 1 from n plus 3, we're going to get n plus 2. If we subtract 1 again, we're going to end up with n plus 1. And I'm just going to abbreviate all the rest of the terms as n plus 1 factorial. So we pulled out the n plus 3 and the n plus 2. The rest can be written as n plus 1 factorial. It's almost like we went to this 5 factorial and we wrote it as 5 times 4 times 3 factorial. That's still another way of writing the same thing, because now we have 5 times 4 times 3 times 2 times 1, which is the same as 5 factorial and the same as what we have here in between. So the nice thing, and you may be able to see now, the nice thing about this is that the n plus 1 factorials now can cancel out. So now we have 1 over n plus 3 times n plus 2. And that's going to be much nicer to find the limit of, right? If we set this up as limit as n approaches infinity of 1 over n plus 3 times n plus 2, there's a couple ways we could think about this. We can just think, okay, the denominator is growing without bound, the numerator staying 1. We can also think about Bobo-Botten, and we have an n squared. So it's a degree of 2 on the bottom if we multiply this together. So we're bigger on the bottom, so our horizontal asymptote is 0. Either way you do it, you get 0. So this, then we could say, converges to 0. All right. So there you have it. That's a brief introduction to sequences and some of the different strategies to find their convergence or divergence. Good luck with the worksheet, and let me know if you have any questions. Thank you very much. Have a great day.